Okay, good morning, everyone. We have no handouts today. A few announcements that I want to call your attention to. Of course, problem set number 3 is due on Thursday. We'll hand out problem set number 4 this Thursday. It'll be due the following Thursday with no late homework because that'll be February 4th. Because we're going to hand out the solutions to problem set number 4 on February 5th, next Friday, because the midterm exam is the following Tuesday, February 8th. So just to kind of advance you on the schedule. The midterm will not be in this room. It's for a couple of reasons. One, we have about 85 students. It doesn't look like that, but we actually have 85 students registered for a class, a lot of people watching on TV, and so it'd be kind of tough to get 85 people in here to take the exam. So it's going to be in the auditorium of CIS. So if you have, I think it's CIS 101, but it's the big auditorium over in the CIS building on February 8th. Now, if you happen to come here by mistake, I'll send you over there because actually I'm going to be doing a tape ahead for February 10th here while you're taking the exam. It turned out it was the only time I could do a tape ahead was during the class period because all the other slots were taken. So I'll route you over there, but you'd be best off probably saving yourself the 5 minutes of having to come here and go directly to the CIS auditorium. So let me just write that down on screen just in case you didn't get it all verbally. 2-8 CIS auditorium. Okay, and PS4, no late. That'll be due. You don't know what it is yet, but just as kind of an advance warning for your schedules, due 2-4. And we'll have solutions due by about noon. The reason for that, having a little bit later on Friday, is simply that a lot of the TV people don't get the help sessions taped. They get them on Wednesday instead of on Tuesday. They're tape delayed. So their homework is due about 12 hours later than the rest of the class. Basically, it's due on Friday mornings, and at that point, we'll put the solutions up on the web for you all to study in advance of the homework. Okay, so that, oh yes, and we have a tape ahead also this Thursday. If you'd like to come, it's in the Skilling Auditorium, which is not too far from us here, and it'll be right after class, so from 11 to 12:15, and that will be for the 2-1 lecture, and it will be on 127. And I'll just have my office hours right after that class, because this is during the office hour period, so I'll be hanging around after that. Usually when everyone catches me is after class anyway, for office hours. Okay, so hopefully everybody has that. Everyone kind of got their schedule down for the next few weeks. Okay. What I would like to do then is cover feedback, and we have an interesting amount of feedback this year in terms of the hours spent. This will be interesting for problem set number 2. We have a huge cluster of students between 3 and 8 hours. Then we have another cluster between 12 and 16 hours. And then we have a final cluster, and there's several students in this category of 20 to 25 hours. So it gives you kind of an idea. There's some, and you could just about guess the comments of this group is, I love the class, I'm doing great, and you know, please give us more. And over here it's like, whoa, hold up, I can't stand it, it's too hard, please, you know, do something to help me. And I think there's some legitimate frustration, I think, in the area of the 20 to 25 hours. A couple of things. I know a lot of the comments were for Ed, the TA, so I have made sure that he gets the feedback also in advance for his help sessions. But you might want to, first thing, of course, you have the resources of the class, the TA, myself, help sessions and such. You might want to try to get some help before if you're out there in your 9th hour and you're still on problem 1, it probably means you should have just started number 2 and forgot number 1, and of course went to the help session to see if you can get some help on number 1. Work the ones that you can or get as far as you can, and then try to make use of us either via email or the various things that are occurring for assistance. What I can do also, and I have done in the past, this is typically prerequisites that are getting the people over here in the 20 to 25 hour category. You haven't had the background in probability or as we move on in random processes is a typical thing to catch people in that area. What I do is, for extra credit, students who are a little frustrated, sometimes they turn that into an improvement for themselves as well as for students in the future. We had those little courselet things that went on a web page. I'll take students who are maybe having a little more difficulty. You can actually help future students the most because you know what you're having difficulty with and what you'd like to see an explanation of. And there may be another student like you in the future. And so I'm open to extra credit projects where if you're spending 20 to 25 hours, you may not have much time for extra credit right now, but at some point, if you'd like to do that and you think you can help, you get some good suggestions or an example that you'd like to see us put on a web page that illustrates some point, you're welcome to do that, and that does help people in the future, specifically on those areas. Okay, so we definitely have this distribution here into the three pots. Some of the specific things that came up is decibels. Now, I've said this a few times in class, but it's coming up again and again. dB are always the same if you take 10 log of a power ratio or a power. Okay, so I'll write power, could be ratio, then you get decibels of something. So if I had a ratio of 2 to 1, that's 3 dB. Okay. If instead I take 20 log of voltage, which is essentially the square root of power, well, let me write this below as voltage ratio, those are equal, and it's the same number. So there's no difference. There isn't a 20 log version of dB and a 10 log version of dB. They are the same always. Never, ever is there two versions. So that is confusing a number of people. It confuses a number of people at this point in the class. Each time we go through, I've said it a few times, but it'll eventually sink in. I think by the end of the class, I find that nobody seems to have this difficulty anymore, but I'm emphasizing it again. A number of people had problems with the TAM problem here. They thought that it was outside the bounds of the class. The idea here was to just simply show you we had gone from one dimension to two dimensions from PAM and QAM, and the square constellations for QAM are very much like the PAM constellations. A lot of the formulas are the same in terms of how much distance you get for a given amount of energy per dimension. So the idea with the TAM problem was to take that further and go to 3 dimensions and show you that you could recast it in terms of 3 dimensions, and you'd essentially have cubic constellations, but they would essentially have the same type of performance as the PAM constellations. And the idea, of course, is you go to 4 or 8 or 16 or however many dimensions you want. As long as you continue to use cubic type constellations, it's essentially the same as PAM. So that was the point of that problem. There is no really TAM used, but the underlying idea was to try to get you to think a little bit about multidimensional constellations. Those do come up in a 379B class, but that's just kind of a simple version of it. So it was really supposed to just make the idea same as PAM. So there was no reason to actually teach that in the class, other than this problem was given to just kind of get you thinking about multidimensional a little bit. Irrelevance, a number of people are still, I think it's basically manipulations of probability distributions here. The basic, whether it's easy or hard, the basic definition, that means you can throw away Y2 at the output of a system. That's it. That's as easy as it gets in terms of representing. Now, whether you can compute these for a given situation or not depends on that situation. But some very nice uses of irrelevance are the reversibility concept. So if the output of a channel goes through a one-to-one transformation, then you can use either the output of that transformation or the input of that transformation. You don't need them both to design an optimal receiver. So that's one great use of irrelevance. The other one was the additive white Gaussian noise channel, going from continuous time to vector of components X or Y and not losing anything. was our second use of the concept. It doesn't really have, for additive white Gaussian noise channels, any other uses that I'm aware of, reversibility, for channels that aren't necessarily in the category of additive white Gaussian noise, though you have to go back to this original description. But there isn't anything quite easier. There isn't any expression I know of that's easier than that to work with. Last thing we came up was energy per bit, which is a concept E sub b, and it's defined as E sub x over b. And someone would tell me, well, other textbooks, use E sub b instead of signal to noise ratio. I think that's a mistake in the other textbooks, and I have seen more quote-unquote experts with a lot of accolades making mistakes on using E sub b. It is useful only, in my opinion, when b is less than 1. If you're using it above that, you're confusing yourself. It's not a concept that really makes a lot of sense. Signal to noise ratio is applicable everywhere. I have never seen E sub b be useful except in this domain. And it is actually a little more useful in that domain than signal to noise ratio is. Signal to noise ratio becomes a little bit more confusing concept. You can still use it, but you have to be careful. This whole E sub b thing is covered in the 379B class because we don't really deal with transmission at very low signal to noise ratio in 379A. You need codes to do that, and codes are in the 379B class. So that's why I'm not using E sub b, even if you've seen it elsewhere. It's usually something that can get you into trouble unless you're dealing with a specific area of coding theory where that measure becomes useful, and it's when essentially, as I should write here, b bar is less than 1, not b is less than 1. Okay, any questions other than that? That's what I was able to distill from feedback this week. And as I said, I've given them to Ed, so he should have them by the very next very next help session, which I guess is this afternoon. So he has that in advance. The topics for today are I'm going to have a little bit of a review momentarily here, but we're going to talk about passband channels. We talked about passband signals last Thursday, so I'd like to talk about passband channels and then passband noise. We went through noise, we went through signals, then channels, then noise, and then finally we're going to put it all together and talk about demodulators again, but in this case specifically for QAM and complex systems. There's a little easier way to do and think of a demodulator when we're dealing with QAM, which is a very common type of transmission method. So we're right in the middle of Chapter 2 now, Section 2.1, 2.2, 2.3. In that area. 2.4 has some interesting stuff on vestigial sideband type transmission, what's sometimes called CAP, Terulus AM/PM transmission. Those are all variants of QAM. They go by different names, so they perform exactly the same, and you can come up with an analysis that's specific to each of those. And I suggest that in Section 2.4 of the notes, but I'm not going to hold you responsible for those alternative modulation methods. If you ever run into one of those, of course, you can always go back, and pretty much everything follows just like it does directly for QAM for those methods. So that's what we're going to cover today. What I'd like to do is just give you kind of a reminder about passband signals. And I'm going to do it in a frequency domain because that's usually the easiest way to think of it. What we talked about last time was a QAM modulated signal. Before I quite get to a passband signal, what I'm going to do is just say, let's suppose I have any signal at all, x of t, which has a Fourier transform x of omega. And I could plot that Fourier transform. Now, if x is a real signal, then x of omega has to have certain symmetries in the Fourier transform. It has to have even symmetry in magnitude, which is basically what I'm showing here. If I were to show the phase, it would have to be some kind of perhaps odd function phase might look like. I got to make sure I draw this right, but basically have some kind of odd symmetry in phase of the function. That always happens for real signals. Now, when I form the analytic equivalent, you remember last time the analytic equivalent in the time domain looked a little complicated. I had to take the signal and then add to it j square root of minus 1 times the Hilbert transform of that signal. But in the frequency domain, if this were, I say, amplitude 1 here, what happens is you just throw away the negative frequency. So I'd have amplitude 2 there. And that is my analytic equivalent. Yes, sir?
Do you care about the phase, or what happens to phase?
Phase remains the same for this the system, because you're essentially multiplying by 2, but not otherwise changing it. So I should really say amplitude doubles. Yeah. Now, if I had a carrier, I'm not going to be able to fit this here on that piece of paper, so let me start with another one. If I had a carrier modulated waveform, it's not going to be nice and centered around 0 like that. It's going to be modulated up to some frequency. That's the idea when we have QAM transmission, is to get it out of baseband, and we're allowed to transmit, or we have a channel somewhere at some frequency, let's say centered around f sub c. And we might have a Fourier transform that in this case looks like that. And because x is a real signal again, then it has to have that same kind of even symmetry in magnitude and odd symmetry in phase about the origin. So if I form the analytic equivalent of this signal, let's say this is amplitude 1 here, again, it's easy in a frequency domain to just simply double this signal out here. So again, around f sub c, and now I have 2, and I get rid of negative frequencies. Okay, so analytic signals are always complex because they don't have symmetry about 0 frequency, and they never have any content at negative frequencies. And yes, you can kind of think of it as taking this negative energy, flipping it around, and adding it over here if you'd like. That's essentially what adding j times the Hilbert transform actually does in the definition of the analytic signal. And if I want to get the baseband equivalent, I want to be able to forget about this carrier frequency here. Pretend this is a channel. It's going to be a complex channel because I'm going to recenter that same signal now about the origin. So what was f sub c now basically becomes dc. And this is still amplitude 2, and this is x bb of omega. Now in this case, we have to be a little careful on the phase. Up here, basically we just had double the signal amplitude. Here what actually happens is x bb of omega is equal to x a of omega plus omega c, which means you move it down in terms of frequency. And if the phase is whatever it was up here at a certain frequency just the right, it's still the same phase down here, but we're reinterpreting that in terms of the frequency itself. So be a little careful on phase if you're thinking about it, but you can always get both amplitude and phase from this simple formula here. Basic idea, though, is pretend this is 0 now. And we're going to have a complex channel, because this is no longer symmetric about the origin. We're going to have a complex signal, I should say. We're about to do channels, and they are the same. We're going to have a complex signal. Its real part is the part that we modulated along the cosine basis function, and its imaginary part is the part that we modulated along the sine basis function. Okay, so we just take those 2 dimensions we were modulating and call it a complex number, and away we go for complex equivalence, baseband equivalence, if you will, of the carrier modulated waveform. So let's proceed and do the same thing for the channel. We're going to be thinking of a signal x of t. Presumably that's a modulated QAM signal progressing through a channel, which is no longer just a, I'm going to ignore the noise momentarily, let's assume that's 0. It's no longer a delta function, so the output of the channel doesn't look exactly like the input. It's not because we've added noise, it's because we've gone through some kind of filtering. Any practical channel, of course, is going to have some band limiting effects. It won't have an impulse response that's simply a delta function, because that's impossible. Okay? You will never have a channel that is truly an impulse. You might be able to get close to that, but never exactly realize that. Now, we have a question before us that if I know I have a complex equivalent of this input, which I can now form, okay, I take the sine part, get rid of the sine in the basis function, take the rest of it, and that's the imaginary part of this. I take the cosine basis function, delete the cosine, and then take the rest of it. Okay, that's the real part of this. And that will proceed through some kind of, put a question mark here, for now, channel, and out will come some baseband equivalent. So the question is, what is the relationship? And it turns out it's going to be a pretty easy relationship. Some of you may be able to guess what's going to happen already for that, just to simply, we're sliding things down to DC, then we should do it for the channel, and